Chemical equilibria. We're going to be looking at it from two particular perspectives. The first perspective is looking at after equilibrium is established here, you're looking at the concentrations of all the reactants and products are going to remain constant with time. That doesn't mean they're going to be an equal amount, but they are going to maintain this same concentration at equilibrium. So as you see in this graph here, you have a reaction of N2O4 by nitrogen tetroxide that is going to break down. We use the double arrows too because it's a reversible reaction now, into 2NO2. They're both in their gaseous phase here. And the reaction's going back and forth. We'll talk about the rates here in a little bit. And eventually establishing this concentration that's going to remain the same after equilibrium is achieved. Now what you should notice about these graphs here is that you're going to have this dotted line part of the graph, and that's telling you when equilibrium has finally been reached. Before that dotted line part of the graph, especially over here at 0, this is initially what you're starting with. So if you look at this graph, initially we're starting with the N2O4. That is the reactant. And as time, you see the slope is decreasing. So its concentration is decreasing. And then also you see the NO2, the nitrogen dioxide's concentration starts to increase. And that's simply because the reactants start to make the products. Okay? So the product concentration should increase. The reactant concentration should decrease if you have reactant making product here. Eventually, though, and you'll see, it's going to start to also where you make enough products, it's going to start making reactants here, and eventually establishing this. You see the flat lines here of their equilibrium concentration. And you notice here the equilibrium concentrations for the nitrogen dioxide, the equilibrium concentration is higher in this particular arrangement here, and the N2O4's equilibrium concentration is lower. So they're not always going to have equal amounts on each side, but what we'll talk about later on too is that the rate of the N2O4 making the NO2 is going to be equal in both directions. The reactants are making products, the products are making reactants at equal rates, establishing this ratio of concentrations. And this ratio of concentrations, we're going to be able to calculate that ratio, and that's what the K constant, the equilibrium constant is. I don't know if you remember that from last year. Remember those K values? And we'll be talking with that. So the first thing to look at is concentrations remain the same at equilibrium. You have a reversible reaction. You have reactants making products, and then the products making the reactants. We use the double arrow here. And you'll see these graphs here. So you have that period at the beginning before the dotted line where it's establishing equilibrium. You have the initial amount, and then the process it's going to in order to establish equilibrium. And then you see the equilibrium concentrations afterwards, after the dotted line. So there's just a bigger version of the graph. Now, what you need to notice too, there's the macroscopic level. And if you're looking at the beaker, and if you're looking at a color change here, because NO2 gas actually is brown. You used it in the copper lab, where you put the nitric acid in the penny and then the brown gas started pouring out. Well, it's brown. So what you could see here is you would see as equilibrium is being established, it starts to turn like brown gas. Well, that's great. So eventually, though, it just looks like brown gas and nothing else is happening. So macroscopically, it looks like nothing's happening. That's what we mean by static. It doesn't look like anything's going on. Microscopically, though, it is a dynamic process. You have reactants making products, products making reactants at equal rate. The molecules are in constant frantic activity. So, although it looks just like brown gas to us, there's actually NO2s combining to make N2O4s. N2O4s breaking down to make NO2s, and it just keeps going back and forth. But it looks to us like nothing's going on a molecular level, because it just looks brown to us for this particular reaction. Some of the other ones have good color changes too. Once again, that color change establishes, and then you look at it and you think, well, it's there, it's equilibrium, but nothing's going on. No, you still have products making reactants, reactants making products. They've just established that equilibrium concentration, so it doesn't look like anything's happening. But it is very fluid situation, very frantic, molecules combining, molecules breaking down, so forth. So I like this slide because it kind of combines everything, and it shows you that different periods of where the dotted lines are. So for this one right here, our dotted line, okay, is right at the initial beginning part. Now the first graph is the concentration graph, the top one. We already looked at a concentration graph. The next graph down below, this is going to be our rate graph. We're going to talk about those in a minute. But it's also showing us our reactant here, N2O4, at the beginning, at that dotted line there. It's all N2O4, right? Nothing really has happened yet. Now as the dotted line has moved over, right? Now we're not to equilibrium completely yet. We're getting there, but as you can see, some of that brown gas is starting to appear into the little tube there. Okay? And also, if you were to look at the molecular level here, you would see that some of your N2O4s have now turned into NO2s. Okay? Like I said, the second graph is the rate graph, so the reactants rate and the products, reactants rate going down, the products rate is increasing, and we'll talk about those in just a minute. But this last one over here, finally, where equilibrium has been established, you can see the definite brown gas in there, because the higher concentration one, the upper one up here, is the NO2, so we see more of that because it's brown. But you also can look at the molecular level here and count them too. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 NO2s in here. And then there's only 3 N2O4s in comparison. So as you can see, the concentration definitely follows the graph there. And you can see it from the little circle diagrams. Like I said, those circle diagrams are very important. They love them on the AP exam. So down here, once again, it's showing you like the overall one you just looked at, and then now this is the rate one, and basically the kinetics, as you see, the reactant rate starts to slow down, the product rate starts to speed up, and then they eventually get to equal rates. In the middle there, this is where they now start to equal each other once equilibrium is achieved. Okay? Very good, kind of throws all three aspects together. You see the rates, you see the concentrations, you see the molecular level, all in this slide. So, changes in concentration. You're given the reaction here. This is called the Haber process, where you're making ammonia from nitrogen and hydrogen. It's a famous reaction. It's used in industry all the time because ammonia has to be put into the fertilizers, and fertilizers are for agriculture, and agriculture is for making food, so it's big business here. So here, this is a concentration graph. It shows us the concentration of the hydrogen, the ammonia, and the nitrogen before and after equilibrium is established. Remember that dotted line's in there for us. So why does ammonia's concentration increase over time here? What can we surmise from our graph here? It is on the product side, so it's pretty much starting out at what? 0. So as the reaction occurs, you're going to start making ammonia, right? You're going to start making product. Okay? So the reactants start making the product. You start making ammonia, its concentration starts to increase. Okay? Why do the hydrogen-nitrogen concentrations decrease over time? Because they're turning into what? They're now combining and turning into ammonia and becoming product. So they're concentration should decrease, as you see, should naturally decrease over the time. And last but not least, if not given the reaction, this up here, if you weren't given this part to look at, sometimes they do that in a multiple choice where they'll just give you this lovely graph here and give you a bunch of things to analyze and ask you a question about it without the overall reaction. And these graphs are really good for multiple choice questions. We're just saying that's a very good set of equilibrium questions comes out of the graphs. What other information can we gather by looking at the graph here? What are some things we could gather from this? Any ideas? Sorry, nitrogen, what? Okay, so that the nitrogen decreases and becomes less concentrated than the ammonia. Okay. Any other things to look at here? There's more hydrogen than the other two. What else can we get from the graph, though? We don't have the reaction. We don't have this top part up here. We don't see this. What can we establish about our reactants and products based off of what we're looking at in the graph? What do we see going on here with the hydrogen, with our nitrogen and our ammonia? We see them establishing their equilibrium concentrations. Good, but before that, what is it going to tell us? Sorry? Definitely which ones are the reactants and products, because you see the ones that are declining in concentration or decreasing in concentration have to be your reactants. Good. So we're going to be able to tell this is a reactant, this is a reactant, this is a product. Good. What else can we tell them? Let's look at our lines a little bit more. Investigate our lines and our... Why was H2 being used more? What did you see about H2 that looks different than the others? Yes? Steeper slope here, right? Steeper slope going on for the H2. That's definitely something to look at. Looking at our slope on our nitrogen. How about the slope on the nitrogen? Not so steep. Definitely declining, but not so steep. What about the slope of our ammonia? Is it as steep as the hydrogen or less steep than the hydrogen? Less steep than the hydrogen, but more steep than the nitrogen. So hopefully you're picking up and being able to see this carefully, but this one definitely, the hydrogen has the steepest slope. And really, as you can see, it's about 3 times as steep as the other ones. So like 3n, whereas this one is not as steep as the other two at all. But the ammonia is definitely in between, right? So this one would be increasing by about 2 times. Why did I put the n's up there? What do the n's mean? What's n a symbol of? Moles. So really looking at the steepness of the slopes, you can kind of tell the molar relationship going on between the reactants and the products here. If we look at our balanced equation, you see that the hydrogen is 3 moles, the nitrogen takes 1 mole to make 2 ammonias. So you can kind of tell some information about the lines, what you're dealing with if they don't give you the stoichiometry balanced equation at the top to use. So you can kind of do that estimation in your head without actually having the reaction in front of you. So do pay attention to the beginning parts, those initials, looking at the slopes. Those are important. Okay? Any questions about that? Does that look about right, though? Like the H looks about 3 times as steep as the N, and the NH3 looks about 2 times in between there. that look about right? Okay. All right. Now, let's think about it in terms of rate. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. So, the products are making the reactants just like the reactants are making the products, but they are doing it at equal speed, equal rate. And like I showed you before, this is the molecular here. So at this particular, for the dinitrogen tetroxide to nitrogen dioxide, they have it going on just as fast. So this one is making it just as fast as that one's making it at their ratio of concentrations that they've established. Just keeps going back and forth, back and forth. It's dynamic, not static. Okay? So our rate graph looks different than our concentration graph. Now these other little k's we'll talk about later when we get to kinetics. This is KR for the kinetics rate constant for the reverse reaction, and then this would be the rate constant for the forward reaction. And we say that the forward reaction is reactants to products, the reverse reaction is products to reactants. So at equilibrium, the concentrations reach levels where the rates are equal. Rates of the forward equal the rates of the reverse. Like I said, it doesn't mean that those concentrations are in equal amounts, though. It just means that the speed are equal. Rates are equal. And once again, you see they have these dotted lines on their graphs to show you before and after reaching equilibrium. So before equilibrium, as you see, the reactant, the N2O4, slowing down. Why is it slowing down in its speed? Well, because products are being made. So the products now are being made, they have a chance to start making reactants. So they're going to start to pick up their speed. So that's why you can see the reverse reaction starts to pick up speed. The forward reaction starts to decrease in its speed till they meet at equilibrium. Nice big one here, showing you once again different, as you can see, this one has a different rate than the previous graph because the equilibrium rate's down here. Now if they actually labeled the axes for us, we could know what the equilibrium rate would be. They told us an actual value. Okay. Good so far? Any questions on that? Yes.
So does equilibrium only work with a reaction that is reversible?
Yes, it only works with reversible reactions, but there are many reversible reactions. Most are reversible. There are, a few that are not reversible, but for our purposes, you'll see a lot of these are reversible reactions. And the reason why equilibrium is so important, especially for manufacturing and industry, is they have to figure out ways to get the output, because instead of it, going just to the products that you want, it will reverse and start making reactants. Well, you want this other product, so you have to be able to control it, make sure that it's giving you what you want with the minimal resources available, like the Haber process to make ammonia. Well, you need high pressure and high temperatures to make the ammonia, and they have this nice big apparatus to do it with, so that they get the most bang for their buck. They get the most ammonia out of the amount of hydrogen and nitrogen required at the beginning. Okay? All right, so back to this graph again, or this chart. Once again, showing you this is your concentration graph. So you'll see them labeled as concentration. You'll see them with the rates graph. And then you see the molecular levels. Okay, so pay attention to all three. Be able to analyze. Make sure you can figure out what you're looking at for all types of these graphs and charts and pictures that they're going to give you. Okay. So for our concept check, a little bit of review of Le Chatelier's too here. So let's think about this. You have a equilibrium mixture in a vessel. You'll hear them placed in a reaction vessel, because a lot of these things are going to just be gaseous, so they have to be in a closed container. So if you see reaction vessel, that's usually a closed, rigid container. You add more water vapor to the flask. How does the concentration of the chemicals compare to its original after the equilibrium is reestablished? And justify your answer. So I'm adding in the water here. How is that going to affect our other things in the reaction? Because now I'm disturbing the equilibrium, adding in more water, and it's going to go back to reestablishing equilibrium. And what is it going to force it to do? Which reaction is going to speed up? The forward or the reverse? I'm adding in water, so I'm adding in more reactant, right? So that's going to push it to the product side. So I'm speeding up the forward reaction. When I do that, what happens to my other reactant in terms of concentration? What happens to that CO as I'm going back and pushing that speed of the forward reaction? Because the water is going to react with the what? The CO. So what should happen to that CO concentration? It should go down. Start to go down. And therefore, what should happen to your hydrogen and your carbon dioxide? They both should start to increase. And it's just going to keep going back and forth until it reestablishes that ratio of concentrations that it originally had. It's going to keep going back and forth until you get that. But we disturbed it, so now thinks it has extra water here. It needs to get rid of that extra water. It's going to start reacting, pushing it towards the products. And then you make more products, so its concentration will be slightly off, so it'll start making more reactants. Once again, it goes back to that ratio. Doesn't mean the concentrations are going to be the exact same amounts they were at the beginning, but it'll get back to that established ratio of how much water compared to carbon monoxide compared to hydrogen and carbon dioxide was originally established. And it'll just keep going backwards and forwards till it gets there. So thinking about this one, you can look at the hydrogen example. If you add more hydrogen, we're adding in the hydrogen this time, what's going to happen? Which reaction is going to speed up? The reverse is going to speed up. It's going to push the equilibrium to proceed to the left, to the reactant side. And I know we used the word shifts a lot last year when we were talking about shifting to the right, shifting to the left. We're going to give you a list of things to say in your pre-response questions and words that they like to see on the AP exam. And they like to say, like, proceeds to the reactant, proceeds to the products, rather than just shifting right and shifting left. I suppose shifting towards the reactant side would probably be okay, but make sure that we're going to give you those, because up until now, most of the free response has been pretty generalized, but now we're getting into specific units. There's specific buzzwords they like to use, and we're going to give you that packet in order to tell you. And there's the talk long, talk wrong kind of thing. You want to be succinct. Get what you need out, but don't go on and on so that you contradict yourself and end up losing the point at the end. So we'll be giving those out to you hopefully next week, so you can start kind of looking at the phrasing to help you word your free responses correctly. So that means what happens to our CO2 up here? It's going to decrease as we're proceeding towards our reactants, and then the CO and the water should increase. Reestablishing equilibrium, the reverse speeds up, then you make more reactants, they start making more products, once again reestablishing that ratio of concentrations that is supposed to be at equilibrium. Because now we're going to talk about that equilibrium constant, that K, that we talked about last year. Hopefully this looks familiar and everybody was shown this equation last year when they were in regular or honors. It's called the equilibrium expression, or the law of mass action. The law of mass action is the fancy, law for it. So if you see that wording in a free response, they're really looking for the equilibrium expression, which is the K expression. And remember, it's always the products over the reactants raised to the power of their coefficients in the balanced reaction. So the chemical species are going to be, C is right here. This is, the one product. D is the other product. The little c and the little d are their coefficients in the balanced reaction. And hopefully everybody remembers what the square brackets mean. Does everybody remember what square brackets mean? Concentration. What do we usually measure in concentration? Or it should be molarity. It should be the big M or the moles per liter. You should be seeing that. That's what's going into those brackets. And K is going to be your equilibrium constant. K does not have units, by the way, so you wouldn't need to label it. It is just establishing that ratio of the products over the reactants, and you can generalize this equation too in a quick multiple choice question where you can see you put the products over the reactants. If you increase the products, your numerator increases, so your K value should go up. If you increase your reactants by disturbing your equilibrium or something like that, then your denominator should increase, and therefore your K value would change and go down. Just depends, and the thing that alters the K values is temperature. So by changing the temperature, you end up changing your ratio of your products to your reactants. That's the only thing that can change that ratio. Everything else, if you disturb the equilibrium, they're just going to keep working back and forth until they get back to that original K constant value, which represents the ratio of the products to the reactants. But temperature can affect K because temperature is like adding heat in, and adding heat is like adding a reactant or product to something. It also changes the rates because it makes the molecules move faster. So temperature can have a huge effect on changing your K value. And that would be the only factor that does change the K value, by the way. So the coefficients become the exponents. That's A. What does a reaction component brackets mean? That means the concentration in moles per liter or molarity. What chemical species have concentrations? This is a good one. Anybody want to take a guess, though, at what kind of chemical species have concentrations? Any takers? No? Oh, before we move on. I just did want to show you this real quick. This is a data table from the textbook where it's showing you, too, that it doesn't matter what you start with. You end up with that same ratio each time. Because you look at the K's over here, 0.21, 0.21, 0.21. Doesn't matter what we're starting with. The first trial run, they start with the NO2. Okay, start with the NO2. Second trial run, they're starting with more of the NO2. And the third one, they start with even more. The last trial run, they're starting with the product, with the reaction here. But as you see, once they get to equilibrium, even though these values right here might be different, when you do the equation, you end up getting this same K value each time, 0.21, 0.21, 0.21, 0.21. Get that same K value, that's the same ratio. Doesn't matter which one you start with, it's going to go straight to those equilibrium concentrations that establishes that ratio. So even different starting concentrations, even different amounts, but the ratio should be the same. That's important to realize. It's a good graphing and data here that you can see that the K value does not change, even though you might start with different amounts. Still is going to reestablish that ratio. So it can be reached from either direction. You can start with the reactant or you can start with the product. Depending on, or you can start with both in there, different amounts of both, but it's going to go back to establishing that K value at the same ratio, products over reactants. Here also showing you that if you're starting with the nitrogen and hydrogen on the left, that was like our first original graph. We still get the ammonia, but the graph on the right is showing you can start with the ammonia and then end up with your hydrogen and nitrogen, eventually evening out in that same proportions. You see each one same proportions, whether you start with your ammonia or you start with your hydrogen and your nitrogen. They're going to go back and establish that proportion, and that's going to be your K value, products over reactants. Now, the chemical species that have concentrations are going to be gases and solutions. So there has to be a certain amount of particles in a given volume. So we're going to talk about why liquids and solids do not qualify under that particular definition. So gases and solutions are going to be ones that have concentrations. Oh, it's going the wrong direction. Hang on. K depends on concentrations of products and reactions. What do we exclude from the expression? We're going to exclude the solids and the liquids. They are pure substances. So basically, you could end up measuring them, and if you use up a certain amount of their particles, you actually end up using up that volume space too, so the concentration really doesn't change for them. So keep that in mind too. So your liquids and solids you're going to exclude from the expressions. Oh, it keeps going the wrong direction, sorry. Now why? Concentrations of solids and liquids are essentially constant. The position of a heterogeneous equilibrium does not depend on the amounts of the pure solids or liquids present, so we're going to exclude them from the expression. And basically this is the gist. The concentrations of solids and liquids can be obtained by multiplying the density by its molar mass, and they end up both being constant at constant temperature. Like I said, so if you take away some of the particles, you're equally taking away the volume, so your concentration really doesn't end up changing, and it stays the same. And we're looking for an equilibrium, definite changes in concentration. So it's very important to realize those pure substances don't have concentrations. They can't be part of the equilibrium expression. They don't have changing concentrations. That's a better way to say that. You don't really need to concern yourself with the fact of being able to calculate their concentrations or anything, multiplying the density by its molar mass, but you just need to remember to exclude them from the expression. So, looking here at particular examples, this particular case you have lead 2 chloride as a solid being in equilibrium with the lead 2 and the chloride ions. Now remember, lead 2 chloride is not very soluble, but those very small amounts of it will, very small amount will actually dissolve in the water. But the solid on the left does not play a role. So the only things you would put into the expression are the ones that are AQs here. And this one has a 2, so we raise it to the second power. It's like putting it over 1 though, since there's no real reactant there. You don't need to write it over 1, but just realize since there's no reactant there, it's essentially over 1. Same thing down here. The potassium chloride is a solid, breaking down into potassium chloride. But you do get oxygen gas out of it. The gas will count. It has a concentration. It does have a coefficient of 3, so you do raise it to the third power if you're writing out its expression. And you would put it over 1. Like technically that's what it would be. I mean, you don't want to write it over 1, but that's really when you're missing a reactant. That's really what it means. And looking here at this particular example, calcium carbonate decomposes into carbon dioxide and calcium oxide. Well, calcium oxide's a solid. So as you can see here, they're trying to show you in this picture, I believe this was in your textbook too, that even though you have a lot of the calcium carbonate, you still have the right amount of carbon dioxide floating around in the jar. The calcium oxide amount might be less, just as long as there's stuff there, though it can keep going back and forth to that equilibrium, keeping the carbon dioxide concentration the same. So down here, this time the calcium oxide has a higher amount. So just while both solids are still present, it will establish that concentration of the carbon dioxide and keep it at that particular same one. So if I were to go in and like remove some of that CaO, still leaving a little bit of it behind, it would go back and forth until it reestablishes the same amount of carbon dioxide in that particular jar. So that brings us to the two types of equilibria, homogeneous, hopefully, or homogeneous. You realize they're all going to be in the same phases. So the Haber process, nitrogen gas plus 3 hydrogen gas, 3 moles of hydrogen are going to give you 2 moles of ammonia gas. They're all gases there, so that is going to be a homogeneous equilibria, or homogeneous, depending on how you like to say it. Another one there is where we have hydrocyanic acid there. Hydrocyanic acid is not one of our strong acids, not one of our strong 7, right? So it's going to be dissolved in water in AQ. Now the hydrogen ions will be there, and the cyanide ions will also be in there. So you have all 3. These ones would be considered homogeneous equilibria. Now if we were to write out the expression, remember K is going to be the products. So I would put in my ammonia, raise it to the 2nd power, right? Over the reactants, my first reactant, nitrogen. And it doesn't have, it has a coefficient of 1. I don't have to raise it to the 1st power. And then my hydrogen, put in its brackets, raise it to the 3rd power since it has a 3 for its coefficient. So that would be the equilibrium expression for writing out that particular one. Down here, once again, you would put your products, hydrogen ions raised to the 1 power, cyanide ions raised to the 1 power over your hydrocyanic acid, and they're all 1 to 1 there, so you don't really have any powers. Remember writing your equilibrium expressions, products over reactants. Yes? What it will do for these particular problems, it'll either give you the equilibrium concentration so you can calculate K, or it will give you K and a couple of the equilibrium concentrations so you can figure out the one that's missing's concentration. And sometimes, too, it will give you the K value, but it'll also give you initial concentrations. This is called the reaction quotient ones, where you're not at equilibrium yet. So you'll figure out which way it's going to proceed in order to establish equilibrium. So there's a bunch of different types of problems that you'll see here. We're not going to get really into like the Rice charts, and because that's a totally new concept until the next set of notes. Yes, they're called Rice charts. It's reaction, initial concentration, change in concentration, and equilibrium concentration. That's what Rice stands for. So we'll be doing those next set of notes, just so you know. So let's look at our heterogeneous ones. I kind of already did one of them in the example there. But here, the only one that would count would be the oxygen. So K is going to be the oxygen raised to the 3rd power. For that particular one, you would only count it. And for the bottom one here, since it's 2 liquid water going to 2 hydrogens and 1 oxygen here, we would only count our gases, products. So K would end up being H2 raised to the 2nd power, and then the times the O2 concentration. Now what would you do if the gas or the AQ was in the reactants only? 1 over it. Very good. Everybody understand that? So if it was only in the reactants, then you'd have 1 over that particular one in brackets raised to its power. Okay? We're good with that? All right. Now looking at different ways to calculate. There is kind of it'll look similar, but not exactly, to Hess's law that can be applied for the equilibrium constant. The equilibrium expression for a reaction is the reciprocal for that reaction. So in reverse, you would just take the K value and do 1 over K with it. And they might give you a series of intermediate reactions that you put together to make the overall, just like you would do in Hess's law. So it's very similar. But in this particular example, it's showing you the 4 reaction N2O4 going to 2 NO2s. And in this particular case, at 100 degrees, the ratio ends up being 0.212. So basically, if you wanted to reverse it, where you start with the NO2 going to N2O4, you would do 1 over that value, which gives you the 4.72. So you can reverse these, and you will manipulate the reactions as well, just like you did in Hess's law, in order to come up with the overall. It's a similar type of calculation here. So if you reverse a reaction, what is the K value of the reverse? It's the reciprocal. You just do 1 over K. That's all you need to know there. If you decide to reverse it, just do 1 over K. Okay? Now, when manipulating a reaction where you are multiplying by a factor, just like we did in Hess's law, where we would multiply through 3. Everything got multiplied by 3, and then delta H got multiplied by 3. Same kind of concept here, except for if you multiply everything by a value, an n factor, then you would have to take your K value and raise it to that factor. So if we're looking here at our original equation, where you just have N2O4 going to 2NO2, that's our normal one. But if you decided to multiply everything by 2 here, now you're going to take your K value and raise it to the second power. You multiplied by 3, you would cube it. Multiply by 4, raise it to the 4th power. Same idea here. So a few little changes when you're dealing with K versus Hess's law, but it's going to be the same kind of idea of taking series steps and merging them into an overall reaction at the end. Okay, so first, if you reverse, reciprocal the K. If you multiply, raise it to that power. The K gets raised to the power. So on number 9, if you multiply a reaction by 2, what is the new K value for the doubled reaction? It's going to be K to the second power. So hopefully you filled in that extra number 9 in there. Apparently it did not renumber it for me. Now, so answering the next question, how is the K of the net calculated from the other 2 reactions? Basically, you're going to do a product of the equilibrium constants. You're going to multiply them. Hess's law, we added them together, right? We just added all our delta H's together. Here, you're going to multiply your K's. So this particular example is showing you a series of reactions. You have A plus B going to C plus D. You have that 1K value, K1. Second step in the reaction, you have C plus F, giving you G plus A. As you can see here, the C's will cancel, the A's will cancel. It has its K2, or its equilibrium constant as well. But in order to get the overall here, you end up multiplying these 2 together, the K1 and the K2. The K of the first step times the K of the second step. So that's kind of how it works. We're going to do an example problem with it right now in the next concept check. So you're going to actually go ahead and look at that particular one and calculate it real quick. So all you need to know here is making sure that if you flip, you do the reciprocal of the K. If you multiply it by a factor, you need to raise it to that power. And then at the very end, when you can cancel your stuff out, you multiply those K values together of the separate series of the steps. Okay? So here, looking at our example, we have two hydrofluoric acids here. It's AQ, so that's hydrofluoric acid, not hydrogen chloride. And we're going to combine it with oxalate. And we're going to get two chlorides. And we're going to get some oxalic acid going out of there. So it gives you the two series of the steps here. The first step right here is just the dissolution of the hydrofluoric acid into its ions H plus and F minus. The second one here is taking your oxalic acid and dissolving it into its ions H plus and the C2O4. We want to make this overall reaction at the top here. That one. So if we're looking at where our reactants and products need to be, any suggestions on what we should do? For the first one, is the HF and the F minus in the correct spots where they're supposed to be. HF is a reactant in the overall, F minus is a product in the overall, so it stays the way it is. Now, does it have the right amounts with it? No. In the series step, it only has a coefficient of 1. Up here, they're both have 2s, right? So what should we do to that equation? Multiply this one by 2, right? Multiply it by 2, but that means what do we do to this K value? We need to raise it to the second power, right? Raise it to the second power. So we can rewrite that down here and have 2HF, H plus, 2H plus, sorry, plus 2F minus, and then our new K. And Kc, if you're wondering what that C means, it just means concentration. Because you can also use Ks with pressures, and we'll talk about that in a minute too. So 6.8 to the negative 4, 10 to the negative 4, let's square that. And we end up with 4.6 times 10 to the minus 7. Check my math, make sure I punched that correctly. Yes? Yes, no, yes? All right, looking at the other one. Are we all in the right spots? No. Oxalic acid, the hydrogen, the oxalate. No, we need to do what? Flip. Do we have the right coefficients for it? Yes, so we're just going to flip this one. So I flip it, and I'm going to put the 2H2 plus the C2 minus 2. And going to put the oxalic acid over here. But when I flip it, what do I do to my Kc for this one? 1 divided by the... And technically, I guess we could just multiply it by this one. We don't have to do it separate. We could just do it all together in one giant calculation. So we really didn't need to do that step separately. At the end, we could just calculate it all together. So 1 divided by the 3.8 to the 10 to the negative 6 times 6.8 to the negative 4 times 10 minus 4 squared. So what do we end up with? What is our value here? Okay, for the overall, for this guy up here, it's going to be 0.1216, so I'm going to get 0.12. Both of these have 2 in their original value, so we're going to go with 2. Remember, K's do not have units. Kind of get the concept. It's similar to Hess's law, not exact. A couple different tiny changes in the rules when you're dealing with equilibrium. Now, you don't have to write this down because it's already in there, but K will always have the same value at a given temperature regardless of the amounts. For a reaction at a given temperature, there are many equilibrium positions, but only one equilibrium constant, one ratio of the products over the reactants, that value number. Equilibrium position is a set of equilibrium concentrations. So as you saw in that data table a couple slides ago, didn't matter what you started with, didn't matter what the numbers were afterwards. When you did the products over the reactants at those equilibrium concentrations, you always ended up with that same K value. You could have more of the product, more of the reactant, but it's still going to be set at that same ratio. Okay? Now, Kc, we talked about just a second ago, involves concentrations. Kp, because we're dealing with lots of gases here, guess what they're going to have? Pressures that you can use. So Kp is going to involve the pressures, Kc is going to involve the concentrations. And on exercise 1, we're going to write out the Kp and the Kc for the following reaction, but we need to make sure that we write out Kp correctly because we're not going to be using concentration brackets since it doesn't involve concentrations, it involves pressures. So there's a different way to write it. And if you do put brackets around the pressures, they're going to mark it wrong in the expression on the AP exam. The brackets are only for the ones that involve concentrations. Instead, you're going to use the partial pressure notation for the pressure ones. So this is how you would do the partial pressures. So you would do the partial pressure of, so if our reaction was, A plus B, C, C, and D. Instead of putting in brackets, you would put parentheses, but you would use the big P, and then you put the little substance down below. In that case, it's talking about chemical species C raised to its power, the partial pressure of D raised to its power, over partial pressure of A raised to its power. So make sure you use the partial pressure notation here, not the brackets. Because like I said, they will mark it wrong on the AP exam if you use brackets when you're supposed to be using pressures. So the generalized look here is just basically instead of brackets, we have these big P's, and then you write the little chemical name as like a subscript. Raise it to the power just like you did before. So we're going to look at exercise 1 where we write them both ways. We're going to look for concentration and pressure since they're all gases in the Haber process. So if I'm doing Kc, I've already did this. We're going to do the concentration of ammonia raised to the second power over the concentration of the nitrogen and the concentration of the hydrogen raised to the third power. That was great. But if I want to do the Kp here, remember we're going to use the partial pressure notation. So now it's going to be the partial pressure of ammonia, okay, that's going to be raised to the second power, over the partial pressure of nitrogen, it's raised to the first power since it only has a coefficient of 1, times the partial pressure of the hydrogen raised to the second power, like so. So this is the difference in how it looks from concentration to pressure notation. Oh, I'm sorry, it is the third power, you're right. I don't know why I put a 2 there. Thank you. Correct, it is third power, thank you. It does have a coefficient of 3 here. Okay, very good. Find the equilibrium constant, Kp, for this reaction. They're giving you the partial pressures of each gas in ATMs. So now, basically all you're going to do is substitute in the numbers and do the calculation, right? So the ammonia, the nitrogen, and the hydrogen. You guys work it. I'll go ahead and work it too, and then we can compare. going to be 39000 or 3.9 times 10 to the fourth. So you'll usually see KPs or KCs written with scientific notation. So you might see it as 39,000, but more likely you'll see it as 3.9 times 10 to the fourth. There we go. Definitely right. All right. Now, between KC and KP, they use the ideal gas law. I'm rearranging it here. So if you notice, here's your pressure. What is the moles divided by the volume represent? What's moles over liters? So that is a concentration. So really, like, this is where you're getting your P, this is where you're getting your C, being derived from. But they come up with this lovely equation for us. Kp equals Kc times RT raised to the delta N. Yes, this is all good types. The delta N is the moles of the gaseous product minus the moles of the gaseous reactant. Notice this one is also a product minus reactant equation. Remember, we always said that the bond energy is the only one that's reversed, where it's the bond energies of the reactants minus the bond energies of the products. As you say, this one still sticks with that normal product minus reactant idea here. Now, here your R value is going to be in the 0.08206 because we're dealing with pressures in ATMs. Now, if you were dealing with pressures in one of the other ones like millimeters of mercury or torr, you would use the 62.36 value. The R values are on your formula sheet. So depending on how your pressure is being reported to you, okay, and the temperature is going to be reported in Kelvin because this is derived from a gas law, so make sure you add your 273. Make sure it's in Kelvin, okay? So a nice little nifty equation to compare Kp and Kc together. So the moles of the gaseous product minus the moles of the reactant here. What happens if delta N is 0? So Kp would equal Kc, because this whole part ends up becoming what? This whole section will end up becoming 1 if delta N equals 0. So do make sure, if you have the same moles of gaseous product and gaseous reactant, that you realize Kp and Kc will equal each other, because your delta N ends up being 0 in those cases. Simple math relationship going on. All right? So, if delta N is 0, that whole section of the equation just goes right to 1. Okay? So now, looking at exercise 3. Calculate the K value for the following reaction using Kp calculated in exercise 2. So our Kp that we just did was 3.9 times 10 to the fourth. We're going to be using that in this particular one here. So go ahead and take a look at calculating that. Yes? Yes. Good. Super huge Kc Because the product moles are 2 right here,
Oh, okay, got it.
minus our total of the gaseous ones is 4. So this would be delta N. And we, as you see, calculated it correctly. Now, what does this K value tell us? This is important. What does K mean? If K is a lot greater than 1, the products are favored in the equilibrium position. So products are going to predominate at equilibrium if your K value is super big. And if your K value is low, tiny, below 1, it's going to be more reactant favor. So your reactant concentrations are going to predominate at equilibrium. So the equilibrium position, you could say, lies to the right. If it lies to the right, it lies to the products, but I would say lies to the product side. You could say equilibrium lies to the left, and that means it's going to be more so on the reactant side of things. But the actual numerical value of K will tell you. What if K was 1? They would be equal. In terms of the equilibrium position would be dead center, equal amounts, right in that middle there, okay? So do understand that if K were to equal 1, it's very rare. I've never really seen a whole bunch where the K equals 1 there. But you do need to be able to interpret large Ks versus small Ks and be able to figure out where the equilibrium position lies. Okay? And, I mean, do think about it, though. You can think about it generally here, because remember, generally products are over reactants are going to be K. So if your numerator is large, your K should be a big number. If your denominator is large, your K should be a small number, right? So if you think about it generally, conceptually like that, it's very helpful to think about whether it's product favor or reactant favored at equilibrium. So the extent of a reaction, this is kind of important. If your K value is much larger, basically we're saying the reaction pretty much goes to completion. There isn't a whole lot of reverse going on here. So K is really, really big, it's pretty much going to completion. If K was really small, then we're going to say it barely gets started. The reaction hardly gets started. Okay? So very small K value basically is going to tell you that the reaction hasn't really occurred. It hasn't really started. There's not much going on there. Not to any significant extent has the reaction actually played any kind of role. So K is super large. Pretty much the reaction goes to completion. So you're basically making all products, hardly any reverse going on. Same is true if the K is really small. Basically the reaction has hardly started. You have tons of reactants, no products, no, can't even really reverse it because you aren't even really making products in order to reverse it. So what does that mean in terms of the K values? Depending on, like that particular one we just calculated was really big. So that one pretty much was going to completion at that particular temperature. Should have been able to see that because that K value, Kc, was super big. So let's look at the reaction quotient. Equilibrium lies to the right. The value of K is going to be greater than 1. There we go. And if it lies to the left, it's going to be less than 1. Okay, good. Make sure we got those down. All right, reaction quotient. The reaction quotient is going to be when you have initial concentrations that are non-zero. Because if something starts out at 0, you know which way it's going to go in order to start establishing equilibrium. So these are when you have the concentrations of everything, but they aren't starting out at 0. And you have to figure out which way it's going to shift to establish equilibrium. So you're going to apply the law of mass action, which is that equilibrium expression again, using the initial concentrations. And you're going to calculate it, which you're going to get this Q value. You're basically using the equilibrium expression to calculate Q from your initial concentration. Once you get that Q value, you're going to compare it to K. And then you're going to be able to tell which way it's going to shift in order to establish equilibrium. couple things about reaction quotient. You have initial concentrations, they're non-zero. You're going to substitute them into the equilibrium expression. And that value that you're getting out of that is not K, it's going to be the Q value. You're going to take that Q value and compare it to your K to figure out which way it's proceeding in order to establish equilibrium. Probably not going to get to actually calculating them. There is a graphic on your notes, though, that shows you which way you'll see it will shift, depending on if Q is greater than K or if Q is less than K. So there's the two different versions. If Q and K equal each other, you're already at equilibrium, so it doesn't matter. But the graphic on there will show you that.